Okay, so today I'm going to basically talk about a method by which a whole bunch of very interesting involutions can occur. And I think that this is really going to be tying together a lot of the things that we've been talking about. We're going to see how involutions of conics are related to things like harmonic ranges. We're going to look at a general recipe to make different kinds of involutions. We're going to look at different kinds of projections of conics themselves, such as the standard ones where you have a couple of fixed points of perspective, and also ones which are so-called potentiazing, where the points of perspective kind of move as you go along. And we're going to look at how these work with more general conics, and what kind of... It's interesting, if you set up the points in certain relationships, certain harmonic relationships, then you can guarantee such things as involutions in the presence of other harmonic properties. So basically this is kind of like a convergence of a lot of material which we've been talking about over the last few lectures. Okay, so what I'd like to do today is to go through a very fast and hopefully informative taxonomy of the different kinds of projections we can do from a circle to itself. So this is very closely related to previous videos, so I'm not going to spend much time on introduction. I'm just going to begin. So we have this axis of projection, and the way this system works is that we have an object represented by a blue point, and we want to find its image. So to find its image is a two-step process. It's a projection consisting of two perspectives. The first perspective uses this yellow point of perspective, so we sort of eyeball the object from the yellow point and we see where it would end up on the purple line. You can think of that as a horizon or something. The second stage then is to do something similar. From this horizon point we eyeball what we have compared with this orange perspective point and see where that maps us back onto the circle, and that gives us the image of our object under this projection. So the questions we're really interested in is, how does the positioning of the primary perspective point, the yellow one, the secondary perspective point, the orange one, and the axis of perspective, the purple line, and the circle, how do those things relate to the kind of mapping we get of the circle to itself? Well, it's nice with GeoGebra because we have a kind of dynamic system where we can just easily move the point around and see where it's getting mapped to. And we can see here that there's two fixed points. In fact, it's general that wherever this purple line, this axis of perspectivity, touches the circle, that will be a fixed point. And you can see as well that what's happening here is it's a sort of attractive fixed point, but it's slowing down as it's approaching it. And here it's the object is essentially pulling the image behind it, and then that reverses. So this is what happens in one particular case where the axis of perspective is cutting through the circle. Now there's one other way this can happen, a distinct way topologically, and that's if the axis of perspective actually separates the two different points of perspective. So in this case we get something a bit different going on, maybe a bit more interesting. So let me rotate around the object now, if I'm allowed to. So notice that now the image is actually rotating in the opposite direction to the object. We still get this sort of scenario where you get these fixed points where the purple line crosses the circle, but they're going in opposite directions, and it's almost as if this purple line is a kind of mirror. Okay? Anyway, forgive me for going quite quickly, but I've got a lot of things I want to cover. So next I want to look at the case, the kind of degenerate case really, where this axis of perspective is just touching the circle, just at one point, if we can engineer such a setup. So what happens here? Well, we have one fixed point here obviously, but apart from that, as you can see, basically our image is just rotating around and around. Whoops. It's just rotating around and around the circle in the same direction. Okay, so finally then, what happens if this axis of perspective is, you know, not touching the circle at all? What do we have happening then? Well, in this case, we don't have any fixed points at all. We simply have that the object circles around. Excuse me, I swing wrong my pen. Yeah, we simply have that the image just circles around in front of the object. As so. Okay, so that's a very, very brief rundown of what happens. What happens when we just have fixed points of perspective. But what I want to look at next is something quite a lot more interesting, so-called potentiazing processes. And the idea there is that as you repeatedly map an object to an image, you're essentially going to be creating new points of perspectivity. Okay, so now I want to show you one of my favourite potentialized projections of a circle, which is a cyclic projection. Basically, we keep drawing extra perspective points around the circle, and we sort of cause a mapping which makes it spin round. Now, it's interesting for several reasons. I find it most interesting because if it happens that you don't make the thing rotate by a rational number, then you can have all kinds of chaotic dynamics occurring. But it's interesting for many other reasons as well. So here's how you start. You start with a couple of points, and you have one of these axes of perspective. And then the way you do it is as follows. You draw a point from the first one, so you use the first line to skewer to draw a point, and then you draw a line tangential to that point. Now you find out where that line meets this axis of perspective, and you draw a line skewering the previous point. Okay, so if we call the point we've just generated t, well, we created t by drawing a line through t minus 2, and now we're drawing a tangent from t and this to the axis of perspective, and now we're drawing a line skewering point t minus 1. Okay, and basically you just carry on like that. So you draw a new point, you draw a tangent to it, you use that to create a new point, you skewer the previous point, you find out where you get a new point from skewering, you draw a tangent to it, you find out where it meets the axis, and so on and so forth. You just carry on this process. Now in this particular case, it just so happened that it all ended up matching up very, very nicely, and I actually ended up getting a proper cycle. Not quite sure how that happened, but in this case I got a cycle so that the thing repeats itself every, let me think, 1, 2, 3, 4, 5, 6, 7, 8 8 projections gets you back to where you started from. But that was just because of the way I positioned the initial points. If I'd positioned them slightly differently, it would have been a whole different story. So this is really a very interesting idea, and it also closely relates to the ideas of things like involutions. I mean, this is what you call a period 8 mapping, because it takes 8 operations to get back to where you started. Involutions are period 2 mappings, which are very interesting because they're closely related to a lot of the harmonic properties we encounter in projective geometry. Okay, so here's a cyclic involution which has some very elegant properties because it basically involves the duality of the quadrangle quadrilateral relationship that I was talking about in my videos on the 13 configuration and such. Just to show you quickly, notice that we have, if we take these 4 points here, that's kind of corresponding to what's going on in here. And then we have the full quadrangle being, the complete quadrangle being included in this picture. And it's all tied up with the way that these points work together. There's several different ways you can label these points or lines to generate an involution. But for a bit of novelty, I'll do an involution with respect to lines instead of points. So what about this middle red point here? Well, I'm going to label this capital M, as is traditional, because what this really stands for is it's kind of like the Briachon point, whereas this purple line here, more like the Pascal's line, okay? And essentially then we have this quadrangle, which you can think of, if you like, as generated by these 4 points around the circle. And notice I've labelled the, quadrilateral. I've labelled the 4 lines of this quadrilateral A dash, B and B dash. So I've put them in pairs corresponding to projections. And now I want to show that this setup corresponds to involution. So let's just consider point A, line A, okay? So what happens to line A? Well, when we look at line A, we see that it crosses with one of these lines coming out of the Briachon point. And so essentially such a line acts as a kind of axis of perspectivity, which causes the line to sort of change direction. And so we go from A to B dash. Excuse me. We go from A to B dash. And now once again we hit one of these rays from the Briachon point, and once again we change direction, and so this time we then go from A to B, like so. And if we then think about what happens from B, Well, when we start from B, we're already on this line here. And so we carry on going until we meet this Briachon point. I think I use yellow now. And then we curl round up here towards A dash. And we do a transition again. And we end up back at A. So that's an involution with respect to A, and in fact by symmetry it turns out to be an involution with respect to all of these points. And what we have here is another example of this kind of process, this kind of potentiazing process where you have two fixed points. I've filled in the numbers and made it a bit more explicit, but basically you can see that as this system evolves, either the points are going to end up getting bunched up towards the right hand side or the left hand side. Now, I've often spoken of projections, and I've often used the circle as an example, but I'm being a bit more adventurous today and I'm using the ellipse. Now, I would like to tell you how to construct this setup. So I'll explain how to set it up to start with. Firstly, you draw a conic. I've just drawn an ellipse here. And then you pick this point, which I'll call big O. And big O essentially generates some lines, which, if you're looking at the line-wise version of this setup, are going to be kind of like fixed lines. I mean, there's two ways to look at a projection. You can look at it as a point-wise thing or as a line-wise thing. Generally, we're going to be looking at it as a point-wise thing. But if you look at it as a line-wise thing, then the meaning of big O is it's where the fixed lines meet. So anyway, that doesn't really matter. Just put this point big O anywhere you like, and then you construct the polar of big O, and that's a line that we call little o. So what is the polar? What is this? Well, essentially you take this point O and you draw tangents from O to the conic, and there's going to be two such tangents, and you find the points where they meet this conic, i.e. here and here, and then you just draw a straight line through those, and that's the polar of this so-called pole. Okay, and then you have some choice, because this is the so-called breathing involution, and basically it's going to involve a lot of points bouncing around, and it's going to involve two different points of projection, which I've called B dash and B dash dash, and they should, I think, they should be separated by this line little o, this line, this pink line here, and also we should have the property that if we draw a straight line from O, we should be able to draw a straight line from O that goes through B dash and B dash dash, and let's call the place where it meets little o, let's call that V. Maybe I'll just label that on here. So this point here, let's give it a name. We'll call it V, big V. So show caption. Okay, right, so what we ought to have then is we ought to have that OV is a harmonic conjugate to B dash B double dash, or in other words that O B dash V B double dash is a harmonic range. And if you don't know what I mean by that, you can look at some of my previous videos. Essentially it means that V divides the interval b dash b dash dash internally in the same way that O divides the interval b dash dash externally. It's a nice harmonic relationship that these things need to have. It's interesting actually, there's a connection between the harmonics, the quadrangles and the involutions. But anyway, so you should pick your b dash and b double dash so that that is true. Now I've done it in a way which is sort of guarantees this truth, because I chose V. Well, I think it guarantees it. I haven't proved it, but I chose V to be the midpoint of the place where this pink line intersects these two places on the conic. And so it sort of naturally falls on this straight line between O and such, and I just checked it out of a calculator, and it does seem as if we do have this harmonic relationship, this harmonic range in this setup. So if you want to be sure of it, you're probably okay by just choosing V to be like the midpoint of this polar little o that's inside the actual conic or ellipse or whatever. And once you've got that, you're basically set up. Now all that remains is to actually discuss how this projection works, and it's pretty standard stuff. The line, the pink line little o, is essentially your axis of projection, and you have 2 points of projection, primarily axis of perspective, and you have 2 points of perspective, primarily b dash and secondarily b dash dash. So how does it actually work? Well, say you have this point here, this is your object, okay? Well, in that case, if you want to find out where the image is, firstly you sort of eyeball where this image point is using this yellow point b dash, and you see where that crosses this pink line here, this sort of intermediate or auxiliary line, I forget which one, but anyway, yeah, this pink line. And then what you do to complete it is you do a second perspective using b dash dash, again lining it up with where you are on the pink line and seeing where that line then crosses this conic. And so you see I've drawn this black line pointing to this purple point here. That's the image of this black point under this projection. So we can move around our object and see how the image position changes. And so this is a so-called breathing involution. It's an involution because basically if you take a point and then you do this projection upon it, and then you find out where its image is, and then you do another projection on its image, you get back to where you started from. So let me just try and convince you of this here. Okay, let's do it like this. So now, well, okay, see where the purple point is, that's the image. Now let's move the black point where the purple point is, and you see that now the image is where the original object was. And if you move it around, you see that basically we could think of this line O, this origin of perspectivity, as something like a kind of mirror almost. It separates things, and we have these fixed points, or double points as Olivia Witcher likes to call them, where this this line crosses. And one can get other various nice pictures by doing traces. So I'll just turn on the trace for the yellow and orange lines. And if I move this around quickly so it doesn't get too messy, you should be able to see. So here we basically see what's going on. I'll take it all the way around. So we've got these kind of rays being projected from these different places. Now, I mean, we're only really looking at half of the story here in a way, because we're only focusing on these point-wise aspects of this projection. But there is, of course, this duality between the points and the lines, and so we can get some nice kind of images of that. What we'll do is we'll get some tangents. Is it tangents we want? Yeah, I think it's tangents we want. We'll get some tangents of these 2 points. So a black line, no, let's use a grey line for a tangent to this point, and we shall use a purple line for a tangent to the other point. So we click the point and click the conic. There we are. So now we have this grey line and this pink line, and now what we're going to do is find out where they intersect. So where do they meet? Well, we just click on both of them and we get their meeting point. Let's colour that in. I'll give it a nice colour, maybe a light green, and let's see how that changes as our object moves. Does it change? So now if we put the traces on both of these 2 things, you can see a very nice kind of family of lines being drawn out, which sort of envelop our ellipse. So there's all kinds of interesting curves you can draw. Turn this trace off now. In fact, we'll hide these 2 lines momentarily. Now what I'd like to do, this is a sort of ambitious bit, is to actually warp this thing. So what I'm going to do in particular is I'm going to mess it up by moving. I'm going to turn it into a parabola, if I can, hopefully without messing it up too much. So if I just shift this point miles over here, let's get the image back in sight. Okay, so we'll go over here, and we're going to keep stretching out this ellipse until it really looks like a parabola. Sort of taking that top side to infinity, that right side to infinity, if you like. Not really infinity, of course, but anyway, looks pretty parabolic now. So let's just concentrate on this part and see what it looks like now. So where's that? There's the object. And now again we can see what's happening with our kind of involution. It's a breathing involution still. And this, so we're still getting this property that, for example, if we find out where the image is of this object and then we transpose them, then now the image of what was the original image is now the object. So we're still getting this sort of involution property that if we do a projection twice we get back to the same point. It's also interesting to see how exactly it works this way. So it projects the image all the way. I mean, this would work properly if it were a proper parabola. I can't be bothered to stretch out the ellipse to make it so, but you see how the image is projected off to infinity and then comes back and then meets again at this double point.